All right, statisticians, in what very sadly might be perhaps the last video in the significance testing series. I know, I'm so sad. I don't know. I might do some more later on the road, but this will be it for now. We're going to compare two types of tests that sometimes can be difficult to distinguish in practice. In theory, they're very, very different, but when we look at particular examples, sometimes we might have trouble distinguishing when do we use each of these procedures. So we're going to talk about a one-sample T procedure for the mean of differences versus a two-sample T procedure for the difference of means. And the key, another name for this first test, which makes it easier to distinguish, is that a one sample T procedure for the mean of differences is sometimes called like a paired T test, right? Or sort of a match paired T test. And this should be reminiscent of a type of experimental design that we had talked about previously in our course when we were talking about how we collect data where we have individuals paired, or sometimes we have the same individual paired with themselves, and we collect data twice from them, and we compare the differences in those results, right? So in this one sample T procedure for the mean of differences, you might have like before and after data, or like say one of the most common kind of go-to examples for things like this might be like something that has to do with like weight gain or weight loss, and you might be like, oh, I have like 10 markers in my hand. What am I doing? Be like, this is how much weight you weighed before, this is how much weight you weighed after, and you're not going to analyze it. So let's say someone before they weighed like 145 pounds and then after they weighed 130, right? What really matters to me is not so much that they weighed 145 and then they weighed 130, but I would care about sort of the difference in their two weights, right? So there was a drop of say minus 15 pounds, right? Say someone else, they started off at 155 and then they got down to 153, that's minus 2, someone started off at like 180 and then they ended up at 181, be like, oh, they were plus 1 and stuff like that. And in this instance, we've got a bunch of paired data because this value and this value correspond with, say, the same individual, right? However, when we have a two-sample T procedure for the mean of differences, the key there is that we have separate samples from separate populations, or maybe it might be separate samples even from the same population, depending on what we're comparing, but the idea is that we ultimately have two samples. In this case, when we have this paired data, even though there was two sets of data associated with each individual, there was actually just one sample where then you would calculate the differences first. And so that's the key distinction when we're trying to decide which type of procedure to use. If we do a paired T test or a one sample T procedure for the mean of differences, the null hypothesis will really be that the mean of whatever differences we calculate is going to end up being 0, right? Versus when we do a two sample, so this is for like a one sample procedure. For a two sample procedure, we'll have a null hypothesis that actually compares two separate means, like that one mean and a second mean are equal, right? In other words, that their difference is equal to 0. So the key idea is that really in the end, there's only one mean we're considering in a one sample T procedure, but there's two separate means that we'll consider. Why? Because if we have two sets of data, those two sets of data come from separate sources. So let's just look at a quick example where we try to see this in practice, right here. A philosophy professor, right? I love philosophy professors. They're wonderful human beings. I should know. A philosophy professor wishes to compare how students performed on the first and second quizzes of the semester, right? The course is very beloved with over 400 students. Must be some big lecture hall thing, or and so the professor simply selects a random sampling of 10 students to compare. Now, I think that clearly this is a philosophy professor is a little lazy. A real mathematician would get some bigger sample sizes. What the heck, right? Is this significant evidence of a difference in the students' scores on average? So here we have quiz 1 and quiz 2. We have a bunch of data, right? And then here we have, these were the averages, right? In quiz 1, the average was 78.4. Ooh. I just realized that this table got the order. This is funny. I guarantee you that was not the quiz average. I guarantee you that was the quiz average. So I think that these columns got all mixed up. Let's just change this around. Whoops. Let's say this is quiz number 1 and this is quiz number 2. Actually, I think that was the case. And then this was the mean. This is the mean, and this is the standard deviation. Funny mistake. I'm not going to re-record this. Let's just roll with the punches, right? I don't feel like reprinting. But anyways, this was the mean on the first quiz. This is the mean on the second quiz. This was the standard deviation on the first quiz. This was the standard deviation on the second quiz. So these sample data do show us a difference on average, but is the difference between these two samples so large that would indicate there's actually a difference in how quiz students scored overall? So just looking at this, just think for a second, what type of procedure do you think we would use to analyze this? Would we use a one sample t procedure for the mean of differences, or a two sample t procedure for the difference of means, right? The difference between two separate means or the mean of the differences that we calculate. Which would we use here? Well, I'll tell you, the answer is, drum roll please, we are going to do a one sample t procedure. This is going to be a one sample t, right? Why is it going to be about one sample? Well, there's first, I'm going to give you a reason why it might seem like it's not that. Number one, the first reason you might not want to do this is because notice that we have a mean calculated for the first quiz and we have a mean calculated for the second quiz, right? I have standard deviation of the first quiz. I have standard deviation of the second. This seems to set up for a two sample procedure. And look, it looks like I have two samples. I have a bunch of quiz scores from number one, I have a bunch of quiz scores from number two. So can't I just simply do an analysis to compare what was the average of this versus what was the average of this? I mean, I suppose I could, and I'd get a p-value and all that kind of stuff, or I can make a confidence interval and that would be great. But that violates a fundamental idea of that two-sample procedure, right? And in a two-sample procedure, when you do a two-sample procedure, right, we need to presume that we have independence, right? That we have independence between and our samplings, right? Really, that all these data should be completely independent of all the data over here. But are they independent? No, we actually, if I look at this, it seems to me like I have a pairing, right? That actually, if I go across, right, this person's this data right here represents how the person did on the first quiz and the second quiz. That like these, I don't know if these are in alphabetical order, what the heck they are, but these quiz scores are associated with each other from left to right. Now, just that alone, just the setup of this table is not necessarily sufficient to say that these data are paired. And it's really the pairing of the data that would give us the one sample t. What else would really indicate it? Well, notice how it's described here. The course is beloved. The professor simply selects a random sampling of 10 students to compare. It indicates in the problem that this is a sampling of only 10 students. Now, if it's a sampling of only 10 students, and I count here, I got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. If these were two separate samplings of 10 each, then my total sample size should have been 20. But in fact, n is only equal to 10. Which is further evidence that this data is actually paired. So what am I actually going to care about here? I'm not going to care about exactly what the average was here and what the average was here. I don't actually care about this. What I'm going to care about is the differences, and that's what I'm going to analyze for my t procedure. So before I do anything else, I'm going to calculate the difference in how the students did from one quiz to the next. So for instance, this student got an 85, then they got an 85. So the actual difference, I'll write the differences over here. The differences in the performance, and I'll do quiz 1 minus quiz 2. The difference will equal quiz 1 minus quiz 2. I'll have the 85 minus 85. The difference was really 0. They did exactly the same. And here I did 75 minus 89, right? And 75 minus 89, that means they actually did way better, right? They actually... Let's see here. You know what? I just realized it feels kind of silly to do quiz 1 minus quiz 2. I'm going to do quiz 2 minus quiz 1. Is that okay with you guys? Are you cool with that? I feel like these numbers are going to be bigger because the average over here was bigger. And so I'm going to do quiz 2 minus quiz 1, but I'm going to calculate all those differences that way. Actually, you know what? I'm lazy. Is it okay that I'm lazy? What I did is I took all these data and I put them in the calculator. If you look here, if I did stat edit, I got all the numbers in the list here, right? And so I enter all this in quiz 1, all this in quiz 2, and L1 and L2. And if I want my differences to be quiz 2 minus quiz 1, I'm just going to go here to L3, right? There's a couple ways I could do it. I could highlight L3, right? And then I can simply see how it says L3 down there. I could say L2 minus L1, right? And hit enter and Shazam. Look, all the differences are right there. So that's pretty cool. Another way I could have done it is I could have simply gone over here and I could have said L2 minus L1 stow into L3. That would have accomplished the same goal. And I mean, I was already there already, but there we go. We have all the differences. So I'm lazy. I don't feel like sitting here and calculating them all or even doing the math in my head. Look, there all the differences are. So what I'm going to analyze is this list of differences. And I'm not even going to write them down because, again, I'm too lazy to do that. But these are the list of differences. And just looking at the differences, do we see what appears to be an improvement? Yeah, across the board, just looking at the differences, I saw 2 students who scored lower on the second quiz, but a vast majority had some type of positive increase, especially some very large increases there too. So if I'm going to do in this case, I would definitely do a one sample t procedure if I was going to do anything at all, right? And so in my null hypothesis, because it's a one sample t, I would start by saying I'm going to define mu d. Mu d is going to equal the difference, right, in quiz scores, right? Or excuse me, the true average difference in quiz scores. And I'm going to say how I calculate it. Quiz 2 minus quiz 1, right? And then my null hypothesis will be that the mean of the differences is 0, that there was no difference between the quizzes. And the alternative, I'm going to, in this case, I just said, is there significant evidence of a difference? So a difference would simply be, stray mark, not equal to 0, right? And I could do a one sample t procedure. Now, I'm going to do this really quick and informally. To do a one sample t, that would mean that ultimately in the calculator, I would just do a t-test, right? And so if I was to just do a t-test, I could just go here. Now notice I never calculated the mean and standard deviation and stuff, but here's a cool trick too. Since I have all the data in a list, I could just go to here to data. And if I say my mu was supposed to be 0, just tell it what list I was working in. So I had all my stuff in L3. I'll do L3 there. I had no frequencies, just keep it as 1. That means every single number in L3 shows up once, right? And not equal to, because I was going to do a two-tailed test, hit calculate and Shazam. I got a t-test where my test statistic was 3.17249, and my p-value was what was it? 0.01132, right? So all that's great stuff. You might ask, I wonder what degree of freedom I would have used here. Well, in this case, since it was just a one sample procedure, we don't need all that craziness for the two sample t-test. The degree of freedom that we would have used would have simply been 9. Our sample size 10 minus 1. So there we go. Now, as an aside, we just jump to going ahead and doing this test, right? Just for fun, what would we have gotten? I'm going to have two things to think about. One, I want to think about what we would have gotten had we have done a two sample procedure, just to see what the test statistic and p-value, just for fun, not because it's actually correct thing to do, but just to compare. But second, I also want to take a step back and think about a step that we skipped here. We jumped right from writing some hypotheses to calculating test statistics and p-values. This p-value is pretty small. We'd probably reject the null hypothesis if we used a 5% level of significance, but we skipped a step, and that step was we skipped checking the conditions. And I want to go back and think about the conditions in just a second. But go ahead. Let's first just see what we would have gotten if we did a two sample t-test. So if I did two sample t-test, where say I did L1 and L2 right there, remember this time, if I'm doing a two sample test, I'm going to not look at the differences. I'm just treating these as if they were separate independent samples. I could do L1 and L2, not equal. Do we ever pool? Answer, no. Hit calculate, and let's just see what happens. Now, notice here, we ended up still getting a small p-value, but not nearly like double the p-value, even though double of 1% is only 2%, it's not that big. It's still a bigger p-value and a less dramatic test statistic, right? And so it would be less unusual, because the idea of this two sample test is if you don't have any pairing, all you're going to really do is look at all these numbers overall versus all these numbers overall. And if I look at all these numbers overall versus all these numbers overall, there's not that big of a difference between them than if I look at the actual differences themselves. If I drill down to individual students and see how individual students did, right, then the difference from one student to the next is actually more dramatic than just looking at these values over here as a whole versus these values over here as a whole, right? And so in this case, it is actually pretty important that you pick the correct procedure. Even though it might have led to the same conclusion, it doesn't fully exemplify the data correctly, because the one sample procedure, in looking at the differences, says, there's a much more dramatic thing happening if we pay attention to the difference between each of these values than if we just look at this whole set jumbled up as a whole and versus this whole set jumbled up as a whole. So that's nice. Okay, so we definitely should have done a one sample procedure, and that's what we did, and essentially this is the way to work out. I said we skipped one thing, though. We skipped checking conditions. And so what are the conditions we're supposed to check here? Number one, we should check randomness. And so let's just do this verbally. In terms of randomness, we do see that this was considered a random sampling of 10 students, right? And if we could check the 10% condition and say, is 10 students less than 10% of all? Well, yes, 10 times 10 is 100, and 100 is less than 400. So this, luckily, this is a very large class, so it would meet the 10% condition there, and that's nice. Though, just as an aside, could we have done this test even if there was no random sampling? And the answer might be yes, if we consider this as a kind of experiment, right? Maybe, right? But then if we treat, in some ways, this was an experiment. Every time a teacher gives a test or a quiz, it's kind of like an experiment. Like, I give you this quiz, let's see how you do, ha, ha, ha. I give you this quiz, ha, 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 let's see how you do on this. And because what makes an experiment is simply applying a treatment. And so potentially we could consider this an experiment. But if we did treat this as an experiment, then we wouldn't necessarily need random sampling, but we'd still need randomness. Where would the randomness come in? It would come in terms of random assignment. In that sense, there should have been some type of random assignment in students to these treatments. We could treat quiz 1 as a treatment and quiz 2 as a treatment. Now, was there random assignment here? Clearly no, right? There wouldn't be random assignment because you can't randomly assign which quiz comes first unless it's like on the exact same content, right? Theoretically, the content on quiz 1 was different from the content on quiz 2. And so if that's the case, it wouldn't make sense to like randomly assign which quiz you get first. But then if you think about it, if treating this as an experiment, this is probably a really junky experiment, right? There's probably a lot of lack of control, right? You can see that there's a lot of lack of control because if this quiz and this quiz is on different content, then simply the nature of the content itself may have a larger influence on why one student's quiz score is bigger than the first, and not necessarily have to do anything with the order of the treatments and things like that as well too. So if, for instance, you gave these 2 quizzes at the end of a course, and maybe they were on different content, but you randomize the order in that case, then maybe this would be a better experiment. So anyways, there could be some problems we thought about an experiment. There's another issue though here, right? Because aside from randomness and all that, we'd also have to check large sample. Now, the large sample condition says that in order for us to be able to use the T procedure here, we need to have at least 30 things in our sample. Do we have at least 30? No, 10 is very small. We only have 10 things in our sample. So what we'd have to do is check the distribution of our sample for skewness or outliers. Now, if we had done a 2-sample procedure, we would have to check all of the data from quiz 1 and all of the data from quiz 2 separately to see if we had any skewness or outliers separately within each sample. But because we did a 1-sample procedure, we only have to check it once. We only have to check the list of differences. So if I go back to my list and I hit stat, edit, and I look here, L3 that had all the differences, what I need to do is to see if this data here, if this data had severe skewness or outliers, right? So let me go here. I'm going to go to stat plot. I'm going to turn it on. I'm going to go and pick a histogram because that's what I like. My data was in L3. I'll keep frequency at 1. And remember, I'll hit zoom, option 9, zoom stat, so that it'll adjust the window and I'll see what I see. I'm looking at that and does it look skewed? It kind of looks skewed to me. It might even be extremely skewed here. I might play with my window a little bit. Like X scale is 3.75. What if I just made that 3? Let's see what happens there. That doesn't really improve things. What if I made it bigger, like 4? That looks less skewed, but now I only have 4 bars. All right, the reality is that these data are kind of skewed. So maybe I should be nervous. Should I have carried out this procedure at all? The real question is, right, does this violate, I can barely read that. Does this violate the large sample condition? When I say, if with this amount of skewness, does this deny that this data could have come from some type of normal population, right? I got this distribution. What did it look like again? Let's see here. Zoom 9, right? That was the guy right there. So if I was to draw this, it would be like down here, up higher, and then lower. You're kind of stuck in a hard place. But in this case, you might actually go ahead and do this. So I would say that this does seem to violate it, right? This does seem to violate. But I might go ahead and still calculate the test statistic and p-value just because I'm a statistician and I like to do that. But I would talk about how this does seem to violate this condition because maybe there aren't any outliers, but we do seem to see there is skewness here. There is definitely skewness. And so I might say, well, since I do see some skewness in my sample, this seems to violate using the T procedure, a T-test. And so maybe I should be cautious about trusting the results. However, I'm going to do it anyways because I like to do math, right? One of the ideas that I mentioned at least some of my classes a long time ago is we mentioned the word robust. T procedures are very robust. And so even if you do have some violations of their conditions, you could still come away with something that's interesting and meaningful. But it's definitely something you'd have to talk about when you're talking about the conditions here. That we do have random sampling, so everything's fine there. We do meet the 10% condition, so everything's fine there. However, we don't have a large enough sample, and we do seem to see some skewness. And so we should be very cautious analysis and using the T procedures here. So if we went ahead and did the test, you'd look at it, you'd have to say, here's a caveat. I'm probably failing to, I am rejecting the null hypothesis here. There is evidence of a difference in students' quiz scores. However, I did violate one of the conditions, so we need to be a little reticent in accepting these results, right? Is that cool, guys? All right, mathematicians, I hope you have a beautiful day, and I'll catch you on the flip side. Peace.